So first I'll tell the device that I'm reading Spanish.
Settings loaded. Ready to shoot. Taking picture.
It displays what it's reading on the screen, so a dyslexic student who can see but can't read can actually read along with the device, and that actually helps build their reading skills. So it tells me it was rotated, but it will automatically rotate the image for me.
Singularidad tecnológica de Wikipedia, la enciclopedia libre en futurología. La singularidad tecnológica, algunas veces llamada simplemente la singularidad, es un evento futuro en el que se predice que el progreso tecnológico y el cambio social aceleran.
And this will translate from one language to another. So I will tell it now to translate to English.
Translation. Technological singularity from Wikipedia, the free encyclopedia. In futurology, the technological singularity, sometimes simply called the singularity, is a future in the event that it is predicted that technological progress and social change will accelerate due to the development of super.
So that's a demonstration of that device.
Ready to shoot.
So let me show you how pervasive this exponential growth of information technology is. It's not just a matter of computerized devices. It really will affect everything we care about. Here, by the way, is a picture of the first reading machine, and this was the size of a washing machine. So the device I just showed you, it's 5,000 times smaller, and it's a lot more capable. The device you're looking at could only read one language, didn't do a very good job, and now reads 16 languages, can help navigate using GPS navigation for the blind. We have technology that actually allows a blind person to navigate inside by recognizing hallways, and has a lot of other capabilities. The rate of change that actually affects all of us, even cultural change, is getting faster and faster because of this information growth that's exponential. And the telephone, for example, took 50 years to be adopted by a quarter of the population. These graphs, by the way, are what are called logarithmic graphs. As we go up the graph, we're multiplying by powers of 10. So every level on these graphs is 10 times greater than the level below it. A straight line on a logarithmic graph is exponential growth. But the telephone took 50 years to be adopted by a quarter of the population. The cell phone did that in just 7 years. And television, radio, telephone took decades to be adopted. The cell phone, the web, the personal computer were adopted in just a few years' time. And I have a whole theory of evolution as to why this is the case. Basically, an evolutionary process, both biological evolution and technological evolution, evolve a capability and then adopt that capability as part of its method of evolution. So the next step goes more quickly. This is a double logarithmic graph. On the x-axis, it's how many years ago this particular event or paradigm shift took place in powers of 10. On the y-axis, it's how long it took for that paradigm shift to occur. So the very first paradigm shift, biology itself, basically the evolution of DNA, that took 1 billion years to evolve. But then biological evolution adopted it. It's used it ever since. So the next stage, the Cambrian explosion, went a lot faster. It only took 10 million years. That's 100 times faster. And then biological evolution kept getting faster and faster. Our species, Homo sapiens, evolved in only a few 100,000 years. That's really a blink of an eye in biological evolutionary terms. And then biological evolution really adopted our species, Homo sapiens, as the cutting edge of evolution. And the next stage, human-directed technological and cultural evolution, went again a little bit faster. It only took tens of thousands of years for the first steps in technology. Stone tools, fire, the wheel. And then we always use the latest technology to create the next technology. So technology has gotten faster and faster. And I put these paradigm shifts on this double logarithmic graph. It forms a straight line showing the continual acceleration in the pace of change. Some people criticize this graph, saying Kurzweil only put points on the graph if they fit on the straight line. So to address that, I took 15 different lists. Carl Sagan's Cosmic Calendar, the American Museum of Natural History, the Encyclopedia Britannica, and a dozen other lists as to what they thought the key events were in biological and technological evolution. And there is some disagreement. You see some spreading of the points, but there's a very clear trend line. No matter what list you use, the pace of progress, starting with biological evolution, leading to technological evolution, has gotten faster and faster. And here I compare a linear progression to an exponential progression. This is on a linear scale, and you can see why they're confused. At first they look the same, because at first you're only doubling very small numbers, but ultimately they diverge very radically. As I mentioned, 30 steps later, the exponential's at 1 billion, the linear progression's at 30. And the pace of change when it comes to information technology is exponential. So ultimately this will transform everything. I saw the predecessor to the internet doubling in power every year in the 1980s. But it was only used by a few thousand scientists. But I saw that it would continue to double. So I predicted a World Wide Web emerging in the mid-1990s, connecting hundreds of millions of people around the world. That was heavily criticized as being ridiculous when the whole United States defense budget could only tie together a few thousand scientists. But it happened right on schedule. And another criticism of my ideas is that, well, Kurzweil takes these exponentials and projects them out indefinitely. We all know that exponential growth can't go on forever. If you have 2 rabbits, they become 4 rabbits, and 8 rabbits, and then 16 rabbits. But that doesn't go on forever. Finally, the rabbits eat up all the vegetation, and the exponential growth comes to a halt. And indeed, we do see that in information technology. But what happens is when we reach the end of the line for a particular information technology, it leads to research pressure to create the next paradigm. And the next paradigm is there when it's needed. In the history of computers, which goes back over 110 years to the 1890 census in the United States, there's been 5 different paradigms. Every time one paradigm ended, a new paradigm was there to continue this progression. And this goes back to the electromechanical calculators that were used in the 1890 American census. Then there were relay-based computers that were used in World War II. Then vacuum tube computers that were used in the 1950s. The American network CBS predicted the election of President Eisenhower, the first time the American networks did that, with computers built out of vacuum tubes. And then they were shrinking the vacuum tubes. Every year they made them smaller and smaller to keep this exponential growth going. That finally hit a wall. They got to a point where they couldn't shrink the vacuum tube anymore and keep the vacuum. And that was the end of the shrinking of vacuum tubes. But it was not the end of the exponential growth of computing. We then went to the 4th paradigm, transistors. And then we went to chip technology and Moore's law. And we've had several decades of that. And so through many different paradigms, this exponential growth has continued. As I mentioned, just in the last 40 years, since I was a student, this has been a factor of 1 billion improvement in the capability of computers for the same cost. Over the whole century, this has been a factor of trillions of improvement. But what's even more amazing is look at how smooth and predictable a progression this is. This is just a very smooth, very predictable progression through lots of history in the 20th century. A lot happened in the 20th century. We had 2 world wars. We had the Cold War, the Great Depression. A lot of other things happened. And you don't see any evidence of any of that through this progression. Even the Great Depression, this progress just continued very smoothly. And this has continued. We just updated this to 2007, and it's very much on target. And I don't want to dwell on all these examples of electronics, but this particular chart here is very interesting. This is the cost of a transistor. 1968, you could buy 1 transistor for $1. Now you could buy 300 million transistors for $1. So you've heard these fantastic comparisons of how far we've come. But again, look at how smooth the progression this is. Look at how predictable this is. And I say this now not just looking backwards. I've been making these forward-looking predictions for 30 years.